last time. Okay, good. So performance, right? So that's obviously very important, because what's the use of the nicest feeling and looking language if it takes you forever? Of course, zero. So that's pretty obvious. So let's look a little bit at that and look at some common pitfalls that make it such that people just grab a piece of code, punch it into Julia, and say, "Oh my God, this is terrible. Doesn't do much better than anything else. So what's the point?" So there's some clear things you should keep in mind when you try to get performant Julia code. And so let's try and figure out what those are. Good. So I mentioned it many times, and I'll say it again. In Julia, you're supposed to write functions. Okay, so even if you're used to scripting and one big script file, put your stuff into a function. Okay. Second, avoid global variables at all costs. Third, pre-allocate arrays and/or avoid too much memory allocation in general. Okay. And don't confuse the compiler by writing code which is type unstable. And we'll see what that means. Okay, but so to start out, why is it that Julia is fast to start with? So what is it that makes it fast? And the main reason that makes it fast is that Julia is at the same time a dynamic language as it is a compiled language. Okay, so it's kind of a weird hybrid. A compiled language is a language like C or Fortran, where you have a compiler that takes your input, transforms it into machine code, and you can then execute that. The dynamic language is something like MATLAB or R, where there's no compilation going on, at least in the base, the base usage of that language, which is very nice for productive working. So you can, you can work on the terminal as we do it. You can explore code very easily, which is very important. But then runtime is not so quick. So Julia is good here because it kind of combines the two worlds. So you can be productive. You can write on the console, you can do plots and do all of those things. At the same time, get quick code, and that's achieved with a compiler that runs inside Julia. The compiler is called the LLVM compiler, and that's just what it is. Okay, so every time you define a function in Julia, the compiler compiles that function into machine code. And the key thing is that this compilation process will take advantage of everything we've said and done so far. In particular, anything we said relating to types. Okay, so you have these different versions of functions, which the compiler will recognize. If you look at your code, it will say, "Oh, here the person is calling this function they wrote and sticking an int into it," let's say. Well, I'm a smart compiler. The LLVM compiler is very smart, as a matter of fact. It knows what specialized instructions your CPU can execute. So believe it or not, on your chip, there's a special instruction for adding 2 ints, and there's a special instruction for adding 2 floats. It's a different operation for your computer. If you know those kind of things, it's good, because you tell the chip, well, here you add 2 ints, here you add 2 floats. Okay? And so the Julia language can do that trick. It will write code such that it fits exactly onto your CPU, and it's going to execute exactly the right, let's say, portion of your compute engine. Okay, so that's kind of in a nutshell why this language can achieve fast code and fast runtimes, and that's it. Of course, I mean, it's like scratching the surface. There's a whole world underneath that, but basically, that's why it runs fast. There's a compiler in the background.
And Florian, you mentioned that the compiler kind of acts on the functions. So the more I use the functions, the faster it is, right? If I try to avoid functions as much as I can, the code is slower.
Yeah, so look, there's in everything I say, there's no generally true thing, okay? Because it always depends. But yes, you should write as many functions as possible, as a matter of fact. Okay, so if you have the choice between writing one huge function, which is very long, and splitting that up into several sub-functions, you should do that. Okay, first, it's going to be easier for yourself to organize and test that, which is something completely out of, Julia considerations, but that's just good practice. Okay, if you have a long thing, split it. There's no cost, there's no overhead. Split it, and because then you can test each little part. What do I mean with test? I mean, well, if in that section you expect if A goes in, B goes out, well, you better be sure that that's the case. And if you split it apart, you can actually test that. You can try it out. So inside Julia, you have unit testing facilities, which allow you to actually perform such tests. Okay, so by all means, yes, the more functions, the better. Okay, you could have the rule in your mind: if something is longer than 3 lines, why not have a function for it? I'm just making stuff up. But in general, yes. Then the precise performance cost of having a long function versus a small function, there's no answer to that. Okay, it will depend very, very much on what exactly is going on. But as a principle, I would say that's a good way to do things. In general, please go to this page, performance tips on the manual. Julia has a dedicated, it's getting longer and longer. Used to be very short, it's getting longer and longer, about tips that people have found out. Well, that's a good principle to adhere to if you want to write fast Julia code. So have a look at those. It's kind of a few. We'll go over let's say the highlights, the ones I think are most pertinent and important for us, but please go back there and look at more stuff. Also, when you have, you're all seasoned programmers, and it's not that there's anything wrong with you. So if you do something and you say, oh my God, this is just twice as slow as MATLAB, what's going on? People are very eager in the Julia community to see those examples. Okay, you have your little example, you put it on Stack Overflow or on the Julia forum, which is on Discourse, and people are very happy to learn from that and and tell you maybe what you did wrong or I don't know what. Okay, so I encourage you to engage with the community. It's a very nice community, very welcoming, and there's no one saying you're stupid because you're using MATLAB. Okay, it's totally off the table. And I'm not saying anything of the sort, if that's not totally clear. Okay, so that said, let's see what we can learn about performance, right? How to talk about performance? Well, we need to know how to measure stuff. Okay, and we mentioned already the benchmark tools package, which is very good here. I will use that. What's also important is, you should know the time macro, which is in base Julia, just for quick timings. That's good enough most of the times, particularly if you have very long tasks. Okay, if that thing runs for 100 seconds, you don't need to take samples. You just, the time thing is going to be enough. What's also very good is the code profiler. That's built in. So you can click on that. It's going to take you to the help of the code profiler. Code profiling is very much in the idea of sampling. Code profiling means to take snapshots of your computer's stack, which is where it locates all the functions and then executes them, okay, as time goes by, and just takes snapshots of that thing and records which functions are getting called most of the time, or which lines are getting executed most of the time. Okay, so it's a very good tool to learn where in your application you're spending most time. Every language that I know has something like that. And right, and so profile view, this package, is a very nice GUI where you can profile a piece of code and then you can look at the graph and click. We'll do an exercise later on where you can click on the part of the graph that is particularly costly, and you learn what's the line in your code that caused all of that cost. Okay, so that's code profiling, which you should know. All right, let's start with those principles. Avoid global variables. And let's just see why that is the case. Okay, so first of all, we don't measure compilation time. Okay, already we did that before. You only want to time the second run of a function in Julia. The first time wouldn't make much sense, not very informative, unless you want to learn how quick the compiler runs. So let's try this out. Let me define a function in a global workspace. So I define it in here.
Sorry, Florian, just a very
Sure,
quick
go
thing. When you mean the first time that you use the function, you mean the first time that you, for example, send to the REPL the declaration of the function, or the first time that you actually give the function an input?
Yes, what I mean is the first time I execute it. So the first time I call it. Okay.
Okay, so, but is it, for example, if it is a function that can take a vector of 1,000 variables or 10 variables,
yes,
for the compiler, it would be the same if I do an example with 10 variables and then...
Exactly right. Very good point. Exactly. Good. Very good point. So that's how you should do it. And we'll do it later on. You'll see. So, you know, if the function that's going to take 5 hours to run, well, make sure you can run it for just 1 second also. Okay, so you're right. It won't give the whole workload. Just compile it once, such that this is out of the way. And then you can see, you know, how the performance is. Of course, exactly as you say, the compilation is not going to be related to the size of the array, right? That's something totally different. It's going to prepare the function, and then you can execute it. Okay, so here we define a function, sum global. What is it going to do? It's going to take in an x. You see inside the function there's no x, so it needs to come from outside. In our case, from the global workspace. So x is going to be a global variable. You see how this works. If there's no x defined, it goes into the calling scope and looks for x. It's like R. Okay, it goes out and looks for that. So what is it going to do? It's going to have s, and it's going to sum for each index in x to s and return s. Okay, just compute the sum. All right. So I'm going to create my global x here. Random numbers, 1,000 random numbers. Then I want to time this. I use the basic time macro of sum global, and I get 0.01 seconds. Okay, and 9.15,000 allocations. Okay, first time around that I do this, you see it reports 98% compilation time. Okay, so that's what I meant. First time you do it, it's not really, you don't care about that. Okay, so forget about it. First time you just run it, and the second time you can actually learn more about it. I call it the second time. Takes much less time, of course, as we suspected, and that's good. So this is the thing we should refer to, but still, you know, over 3,000 allocations in order to do that here, which sounds really strange. Okay, and in fact, there's something wrong. That's not the way it should be. Right, because there's nothing to be allocated. There was no array operation, nothing. So it's really weird. So whenever you see that, allocations that should not happen, it's a sign of a problem. It could be that there's many small temporary arrays being allocated because of what you're doing. Okay, for example, in our case, it could be that it takes chunks of this global x, copies it into the function, sums over it, does stuff like that, which we didn't intend to do. Okay, and so that's where this is dangerous. So let's pass x as an argument instead. Okay, let's do that as it's supposed to be. So here goes x, new function sum global arg. X is still a global variable, but at least I can now pass it by reference. All right, do it again. Okay, it takes like almost nothing, and in particular, there's nothing here. There's no allocation. Okay, no memory is moved. So that's the first takeaway. Never use global variables from the global scope. Okay, if you have to, then pass them as an argument. Okay, that's the first takeaway.
Quick question.
Yeah.
Can you go back to that function? If I define s as 0, is that too bad in terms of performance, or instead of 0.0?
Yes, very good.
Messing integers and doubles.
Exactly right. It is very bad. So we'll see that later on. Okay. So what you just said. Okay. We'll see that. Don't worry. Very good point. Here we go. That's the next example. So the JIT is the name for the compiler. It's called just-in-time compiler. The fact that as soon as you hit enter, the compiler starts and does stuff without you ideally even noticing. Okay. Sometimes it takes long, but most of the time it goes fast. So we need to help this guy. Well, at the very least, we shouldn't confuse him unnecessarily. How can you confuse a compiler? Well, it's kind of straightforward. It's exactly what we just said. So Luis just pointed it out. Here's a function that I call unstable, in the sense it's type unstable. All right, I have an x here, which is an int, exactly as Luis said. It's just a 1. It is an int. Y is also an int. And I loop over this 10,000 times. And each time I do something to that x here. In particular, I divide it by a random number. The random number is whatever it is, but the division by default is going to create a float, right? If you divide something, most of the times you end up with a float. And so at that point, you convert the x, which was an int, into a float. I added a second variable here to make the problem more severe. So y is just also there, and also sets up the compiler. Okay, so let's verify what's going on. We have those 3 data types. What's the type of 1? It's an int. Type of 1.0 is a float, and type of 1 divided by something is also a float. Okay, so that's what's going on here. And that's not going to do very well. So I need to re-execute those benchmarks every time, which I actually don't know why, but that's what I have to do. And then let's see how long that takes. So BU for benchmark unstable. Okay, so that takes 31 microseconds, 0 memory allocation. Okay, fair enough. That goes pretty well. Next, we have the stable function. Stable function is exactly the same. So like Luis said, the only thing I'm changing is I'm adding 0.0 there. Everything else is copied. It's the same thing. Let me run it again. So I'm running the benchmark on the stable function, and then we can compare this. Okay, so this is it's 26 microseconds, so slightly less. Okay, and so you think, okay, it looks like a tiny difference, but if you compare the two, like, you know, what is the actual performance difference is 18%, you know, from such a stupid thing. So, you know, a minimal change in the code, 0.0, is going to have a pretty big impact. Okay, so imagine that would be a very big function with much more different inputs and more workload. That would definitely start to hit you. Okay, so you want to be very careful that if you do such kind of things, don't trick the compiler. Stick to a data type. And, you know, in many of our operations, it's pretty safe if you have these loops to initiate them as a float. Okay, so it's just something to keep in the back of your mind. Okay, that was one thing. There's a very nice macro that helps you here, because of course it's hard to think about everything, given you have to think also about what you actually want to do. And so this macro is there to help us. It's called add code _ warn type. And so we can just call that on our function, like we do here. I say add code warn type unstable, and it goes through the function and it checks whether there's a type instability, and it's going to return them as red in case it finds one. So look, for example, this is very hard to read because it's basically assembler. So this is actual machine language already. So it's very low level. But you know, you get some, well, first of all, you see the colors. So that's kind of easy. And you will get used to it. Okay, so we're not going to go through what this all means, but you can kind of figure out what it means. You know, so these are the line numbers, 3, 5, 6, and so on. And so it's very, this is what the computer does. Okay, so this is what the computer is going to understand. Once you hit enter, that's delivered to the chip. Same thing with all other languages, by the way. Okay, a computer executes that kind of stuff. A computer never does anything that MATLAB says. Okay, MATLAB is going to take your code and do that. Okay, so it's the same thing. But basically what we see here is that, oh, there's the red stuff going on. And the red stuff tells us that X and Y are basically not one type for the compiler. They're actually 2 types. Because you told him that you want to start as an int. So he's going to say, okay, here's X, that's an int. Then he goes along, he looks at what you're trying to do and he says, oh my God, this guy is going to end up with a float. And so he's going to specialize the code for a new type, for a union type, you see? So the code he's going to generate is this one you see, and it's a code that works for the union of float and int, okay? And again, you know, this time it cost us 18% performance, which is already pretty hefty, but that can get much worse, okay? So that's a very cool macro, which is very easy to use. You just put that in front of your function, see whether it gives anything with a color red, then you know, okay, I need to check that. Okay. Good. Avoid working in global workspace. Avoid working in global workspace. Well, I guess there's an in missing. Okay. Avoid working in global workspace. We mentioned that many times. Use functions instead. Okay. Why is that? Well, because everything in global scope is type unstable. So everything you do in global scope is going to be confronted with the problem we just illustrated. And you don't want to have to think about that all the time. Why is everything in global scope type unstable? Well, because you do that, right? You can do that in global scope. We did it many times. First of all, I have a z that's a number. And I say, what is z? It's 1, it's of type int. And then I just say, well, now z is a what? So it's a string. So there's no way for the compiler to do anything. If you work in global scope in Julia, you might as well work, forget about it. Because there's no, in terms of performance, there's nothing the compiler can do. Okay, you can make no assumptions about what you want to do with that stuff. Because once z is a number, once it's a word, so I mean, how could I write specialized code for that? Okay, so stuff needs to go into functions. What is this? The compiler can't rely on anything. Let's try this out. Okay, something needs to be redone here, I guess. Okay, so what am I doing here? I have two vectors, x1 and y1, and the number a, which is 0. Then I have b bad, benchmark bad. Okay, so here I'm doing some stuff in the global workspace. I want to do this particular summing operation, sum to a, square of x1 and square of x2. Let me run this. And I want to benchmark it. Okay, so I do this for the length of x. I guess it should be length of x1. Anyway, thankfully they were the same length, so that worked. Okay, here's what we get: 170 microseconds. All right, fine. Let's see how we could do this otherwise. Let's create a function, local function. Okay, that function does exactly the same, so that line is exactly the same. What's different? Well, different is just that those get passed as arguments, x and y. We start with 0, with the 0 element of the data type in x. Okay, so we can be very generic here. If the array has ints, that function will be specialized for ints. If the array has floats, it will be specialized for floats, blah, blah, blah. Complex numbers, it will run for complex numbers. Okay, then let's see what be good is going to do. So let's run the benchmark for good using the local function. Now, what is this? Like, totally blows it out of the water. Like, it's again compared with the judge function. Like, that's just incredible, right? What is this? 21,000% faster. I mean, don't even know what that means. So there's no way that you ever, will have good performance working in global space in Julia. It's just a no-go. Okay, good. Pre-allocate output. So that's very relevant for us, actually, right? In our applications, we most of the time have something that represents some kind of model, or there's a data structure that needs to be filled out with values. So for us, it's always a good idea to pre-allocate these arrays. Particularly, you have to obviously do something on them many times over. So think of an iteration or something. You don't want to have to create the array each time that you come out of the iteration. It's much better to have an array that's there for this purpose and you override it all the time. Again, let's look at an example. Let's do something like a matrix multiplication. And let's have two versions. In one version, we return the result, like a new matrix. And in the second version, we have a matrix that we want to write into. And then we just want to see the time difference of doing those two things, which are doing equivalent operations. Okay, so there's going to be two versions. Version 1, version 2. The difference, as I said, is that version 1 will, at this point here, create a new matrix. So how does it work? It takes the number n, it will create A, it will fill an n by n matrix with random numbers, call it A. It will fill an n by n matrix with random numbers, call that B. So there's two identically sized matrices, and then it will do A times B, so matrix multiplication on A times B, and then do a sum on it. At this point here, this function creates a new matrix. Okay, has to create a temporary matrix to then sum over it. If you pre-allocate this is different. So that's called the second version, rand mul with an exclamation mark to make explicit that we will write into C. Okay, we'll do it differently. So we have A, which will be passed in, filled with random numbers, B, passed in, filled with random numbers, and C, which will be passed in, which we'll write into with the mul function. Okay, that's a special Julia function that
in this case, sorry, Florian, the fill function takes care of the size of A and the elements that rand has to generate, I'm guessing, no?
Yes, exactly. So here, fill takes an existing A. So again, there's the exclamation mark, which is going to tell you I'm going to modify the object you give me. You give it A, and he's going to fill it with a value, which is going to be rand. So it's going to call rand.
What I mean is that this rand is applied to all the elements of A, right?
Yes.
Okay.
So actually, I don't know if it fills it all with the same number or not. I guess it does. Otherwise, that wouldn't make much sense. So let me say A0 is zeros 2, 3. Let me fill that with A0 rand. Yeah, all this the same number. Okay, it's a unique value. So you say fill with the same value, the one value that you fill it. Okay, so the fill function, I now remember, takes one value and gives it to all the elements of an array. That's the definition. So that does the same up here. Okay, it draws a rand and it puts that into all the elements of the array. Okay, so that's going to be the difference. Again, the difference is going to be that we don't have to create C. C comes from outside. Okay, it's a bit of a contrived example, but anyway, let's see what it's going to do. So we have n as 100, so 100 times 100, a reasonably sized matrix. So we create the arrays outside A, B, C, and then we trigger compilation once of the normal version and of the pre-allocated version. And then we want to see what it does. So again, my benchmark tanked, and I don't know why, so we do it again. So this version is the version that creates the output object. Okay, that's what it takes, 154 microseconds and a bunch of allocations, of course, because it has to do all of this memory business. A good is going to be much better, of course, and we'll see. Okay, 0 bytes allocated, because of course the function itself didn't do any allocation. That's how we wrote it. And you look at the judging function, so it's much faster, and there's no memory comparison possible because you compare it to 0. Okay, so if you can do pre-allocate stuff.
Florian, but this seems to be like a specific pre-allocation. We are pre-allocating C outside of the function.
Yes. Yeah, we're pre-allocating everything outside of the function. A, B, C. Exactly.
So if I don't plan to use a temporary matrix, I don't need to pre-allocate it outside of the function, right? If I want to use a matrix only inside the function, for example.
Yeah, so it always depends what you want to do. So suppose you just want to compute the sum of a matrix that you give in, then there will be no, if you just forget about all of this A-B stuff, you wouldn't have to pre-allocate anything, I guess.
Yeah, for example, I would think that I would need to, if you said, oh, pre-allocate C, I would do the following. I would create C as a zeros inside the function that has the length that comes out of this operation. This would be not the best way.
No.
You need to pre-allocate before calling the function.
Yes, because I mean, you want to do it like this.
Yes.
Right? So that of course allocates 100 times 100 numbers, right? And so I mean, there's nothing wrong per se, but if you call randmol many times, that's just time lost, you see? So much better to keep C outside, override it all the time, and do it like that. Okay. You need to think a little bit about this, but once you get that, so just keep into your mind that creating arrays is costly. It just takes time. Like obviously, you just think about it a little bit. Your computer has to go into RAM, find a spot, load up these bits. It's just stuff that takes time. Okay. So we want to avoid it. Okay. All right. That's the last thing. So let's try this out, or go all the way to the end. Oh, I passed it again. Come on, man. I'm not going to scroll there now. So, okay. So here we have a little exercise. Can't let you go without that. We want to use the profile view package. Okay, let's try this out and see if we can get this running on your VS Codes. So here's a little test function, which is going to do a bunch of array operations. Okay, because those are kind of costly in terms of indexing and moving stuff around. So it does a bunch of things, and we want to understand where exactly it spends the most time. Okay, so from looking at it, it's going to be very hard. We have no idea where we lose time, etc. So let's do the following. Everybody creates a file in the VS Code .jl, and we're going to start the top. We're going to write using profile view. First, you have to install it. I guess that's the second point. Install profile view package. I hope you remember how to install a package with the closing bracket, and you say add the package name. And then you would just, compile it once, exactly as Luis before said, or no, Rafael, was it? You call it once with a very small argument. Okay, you just do it for n = 1, just to compile it once. Then you can look at the text output of the profile macro, which is going to print a bunch of lines and tell you how often did it encounter those lines. And then finally, we want to look at the output of this thing, which is profile view, which is going to give this graph, where we can then navigate through and click on the line that is the most costly and find out where it is in our function and fix it maybe. Okay, so let's try and do that. I'll put you into breakout rooms, and then we'll see what this graph looks like. All right, let's go. Okay, you guys were able to install the package?
Yes.
Yes. Okay, brilliant.
We got very ugly output.
Yeah, it takes a little bit of practice to read the output as well, but already that it worked is a success. So okay, so right, so here's this function. You had just to add those two lines, copy this over, precompile it once, run the profile function by itself. So if I just execute that, well, we don't see anything. Why not? I see, because it's stored somewhere. So then you have to do profile print, and it's gonna dump all that stuff out, which is very hard to read. But basically, so this is the output of the profile process. It measures how often each line is basically visited. You see?
We got like a graph with lines.
Yes, no, that's much better. So I'm getting there. So this is just to illustrate that the profile function generates this kind of data. Okay, and now the graph is going to grab this data and make it a bit more digestible. Okay, so if you call that function here from the profile view package, you were supposed to see something like this, which has a fancy name. It's called a flame graph because, well, I don't know, maybe it looks a little bit like flames. And so the way to read this, you can, if you go with your mouse, you hover over it, it's going to tell you what was done. So at the bottom here, this is all not interesting. This is all what's needed in order to run a Julia application anyway. So this is total nonsense. You can't do anything about that. If you go up, at some point, and particularly you'll see that when the line is no longer just one color, because the color says how many operations you have. So this line here is going to be start interesting for us. You see, there's fuchsia, green, and pink, and so that's our three main lines in terms of cost. So line number 9 is here. Okay, so that guy takes a lot of time. You see, it's the widest bar. Next one is 7. So that's 7. Okay, so this one takes a lot of time. That one takes a lot of time. And the last little bit here is 11. 11 sorting takes much less time. Okay, so the map slices is the one that takes most time in this little example. Then you could, then if this function goes on, you could look, well, what is it actually in that line that takes so much time? And you go up, you see where you're going to spend all this time. Okay, there's in the reduced bin JL line 889 is going to do all this work. You can go out and see what. Sometimes if there's a certain problem in your code, you may be able to figure it out like that. Okay, so you have somewhere you do that with your code and you see, okay, at that line I spent so much time, I don't actually understand why. Then if you go into a flame graph like that, you'll be able to maybe understand more, or at least it's another tool that you have available. Okay, so you may want to use that and try to think about these things. Questions about this graph? Any questions? No. Okay, so well, that's just for you to know. So there's some things that you can try out with these tools. Okay, so that was the end of the performance thing. Yes, so we can go back and go to the almost last lecture that I prepared. And what's that going to be? I think now it's time to do some plotting. So that's going to be fun. Now we can finish up with some interactive plotting. So I think we're just about right with the material I prepared. It's not too much. Not too
Florian, just one quick question. If you could point us to how to do debugging, for example.
Yeah, very good question. Yeah, very good. Excellent question. So that's a good idea. So let's just do that right now. Yeah, let's just do that. So look, here's a typical thing. So you would have a JL file with some stuff in it. And so let's just do one thing. Let's just do this for 10. And I'll comment out the rest because I don't want to debug the this. Okay, you would save this. Very good suggestion, Rafael. That was a good idea. Okay, that's fine. I don't need this. So now I'm ready to debug this. So here on the left, you see there's a run and debug function on the bottom. You click on that, and you just do run and debug. It's going to debug this file. So let's just do that. Okay, so it's going to start a debugger, connecting to debugger. Done. Okay, so it's switched color. You see it's now orange. It means it's in the debug mode. So I can go here to this second console, debug console, and I'm in this file now. So is it still running? Wait a second. I'm just very busy on my computer right now. Let's stop. Okay, I'm not sure that was the right thing to do. Let me try again. So one way that definitely works is okay, of course it runs. Yeah, I see. So there was no reason for it to stop. So it just runs this function and stops. Okay, of course you have to set a breakpoint. Otherwise, what's it going to do? So let me set a breakpoint here at this line. Just click in here in the gutter. That's going to do that. And let me run it again. Okay, so I go here, restart. You see it picked up the breakpoint. And you see it's running. So the first time you do that, it always takes some time because it has to undo your code and I don't know what. Yeah, that doesn't seem to work. I don't know what's happening. So I don't seem to remember how to do that properly.
I followed the same steps and I think it worked here.
For you, it stops at the breakpoint.
Yeah.
Yeah, for me too.
Just so my computer is like going completely insane with all of this streaming going on. Maybe it just never finished to do that. So anyway, so you got the idea. You just set a breakpoint. You make it run the file. Of course, you have to execute the function, but that's fine. It goes into it, and then it works. So let me try something which usually works. So I can do add enter and enter a certain function directly. Okay, then I can't set breakpoints, but at least I can traverse the function. Okay, so I'm here now, and I can go inside the function now, step in. Okay, so now I'm inside the function, so you see I can't set a breakpoint. Maybe I can set one now, but anyway, I can now step over this. Okay, and I can at least show you some cool stuff. So because here you get the local variables and all of that nicely sorted for you. So step over is going to take a step to the next line. Okay, so then you could, if you wanted, you could go inside the rand end function, which I don't want to do now. So I'll go over it. Did I click?
But sorry, one question. When we put the breakpoint inside the function,
Yes.
does it wait until you call the function with an argument to stop in the breakpoint, or is it a breakpoint that so that before you send the function to the compiler and so on?
No, so I don't know exactly how that works. It's actually quite, I've got no idea.
I mean, because what I would do in MATLAB, I would call the function, put a breakpoint there, and then I would go into that function after I call it, no?
Yeah, so see, that's what I did here, right? So,
Okay.
so in the same way, you would set the breakpoint and call the function again, it would stop at that point. So in that sense, that's what it does. You need to execute the function, right? Otherwise, you can't reach the breakpoint, even with MATLAB, I guess. Okay, but so anyway, so what's kind of cool in VS Code is this panel here where you can track what's going on. So you see it shows me what I did so far. So A is now this array. You can look at the array and all of the first 10,000 numbers in that. So it gives you a nice split view of all of everything that's inside this A array. You can check whether that's what you want, and so on and so forth. Again, you can go over this. So it's kind of cool. And you can have watch conditions. So that's very nice. You can say expression to watch. So tell me what the index I plus 10 is. Okay. So as you know, you can do stuff like that. So you can do on the fly computation while you're in the debugger. Because it's really very, very cool the way it works. You can also change variables while you're there. Yeah, so you can for example, you can change n, for example. Okay, look at that. And for a compiled language, I'm quite excited. So the loop, the function is defined for I to 10. What if I want to run it for I to 12 now? I can just grab this, change it, and the debug session is now going to run for n up to 12. Okay, so that's very, very powerful for a compiled language. There's no way you could do that in C++ or Fortran. Okay, and then well, you go and you go into one of those and you check out where the bug is. Okay, so for me, the enter works quite well. I'm not sure what was wrong with the breakpoint. Maybe I was just too impatient to wait for it. But basically, that's how everything works. And that also works with your own. You know, if you have a package, you can debug in the same way. Just you would have the name of the package in front of this, and you would enter that particular function of that particular package that you want to debug. Okay, so thanks a lot for that pointer. That's very important. So you can actually debug in a pretty reasonable way in Julia with VS Code. It's a kind of a new addition to the functionality, to be honest. So that like a year or two ago wasn't so easy as it is nowadays. Okay, cool. Right, so we've got a bit more than an hour to go. I think that's just about right. So we can talk a little bit about plotting, which is kind of easygoing. So you can relax now. And then we get to do half an hour with this, and then we can do half an hour with some interactive plotting, which is kind of fun as well. And then we can talk about whatever you want until it's 4, and you know, to see what other stuff is interesting to you. Of course, there's so many things that I did not talk about, but that's just the way it goes. I'll put
maybe if there is time at some point, I have like we made with Luis and Rafa a little simulation of Solo. If
yes.
You can have a look and say if it's efficient or not efficient or what.
Yeah, well, now you can measure that yourself. No, you have all the tools. You can.
Yeah, but not.
No, for sure. We can have a look at it.
Okay.
Okay, so I mean it's 3 minutes to 3. Let's just make a quick break. Okay, let's do 5 minutes break, and then we'll go for the last mile. Okay.
Okay, thanks, Florian.
Okay, see you in a bit.
Thank you.
One sec.
Hello. Your camera is on.
I forgot to put it off. Okay, thanks.
All right, guys, I'm back. So are you? Some of you? Okay, so yeah. Hey guys. Okay, so let's do a little plotting, which is going to be fun. So I load a couple of packages in the beginning, but you know, that's you'll see that later on. What that does, it's not so important. First of all, in Julia, there's many ways which you can make a plot. So there's many plotting packages, which in itself is good because you can choose whatever is much to your liking, but can also be a bit confusing because you don't actually know, you just want to make a plot. How do you make a plot? Why if there's 50,000 ways? So I will choose to just show you one package, you know, with the potential downside that that's not your favorite choice, but you'll have to make that choice yourself. So on that GitHub organization, you will find all the plotting packages. Let's just quickly go there. So here they collect all the different packages. Okay, so plots.jl being, let's say, the most widely used one, the one we'll use today. I'd like to point towards Maki, which is widely regarded as the future of plotting in Julia. So keep that somewhere on your mind. It's a fascinating package. I was on the fence of whether I want to show you this or the other one, but I'm not as good with Maki as I'm with the other one. So there was a slight risk that I show you stupid stuff. So here's a few others. Gadfly is very good. Gadfly looks a bit like ggplot in R. Okay, plots, we'll talk about that now. And Maki is a very cool thing. It's extremely powerful. So, I mean, just have a look at it. Right, what is plots now? Plots.jl is, well, you can call it a non-traditional plotting library in the sense that it does not implement the plotting backend. So it doesn't come with the code that actually makes the picture. It's just something that makes you call different backends. Okay? So what does that mean? Well, so it means that, for example, there's one backend that produces PGF plots, which you can include directly as LaTeX code in your LaTeX file. So it's not a picture, it's actual tech code. Okay. So if you want to plot like that, usually you would have to learn the API for the PGF plots package, okay, which says you make a plot like this and that. Then you want to have a simple picture of your plot. Well, you can't do that with that package. So you need to work with another package. Okay, so the cool thing about plots.jl is that you don't have to worry about this. There's one API. It tells you a plot, you make like this and that, and then you choose who produces it for you. The thing that makes a picture, the thing that makes a tag file, or I don't know what. Okay, so that's going to be the philosophy here. And we will just work with the default backend. Okay, we don't have to worry about that. So there's a default backend which works very well for our basic applications, and that's it. Here's a list of all the backends. So look, there's quite a few, right? So PyPlot, for those of you who do some, that's, you know, matplotlib, basically, that's the Python package, very, very mature, does a lot of stuff. GR, that's the default backend that we'll use, very good. Plotly.js, you can do interactive graphs and web stuff. PGF plots, I just mentioned, that's native tech code. Unicode plots, you can make plots even in Unicode, so that's going to display on your terminal. Don't need a plotting window, as it were, and so on and so forth. Okay, so if you want to know more about this, click here on About Backends, which is going to tell you how that all works. Okay, that out of the way, let's make a plot. So I would actually recommend that in your REPL you say you want to add the plots package, such as you can keep up with me. So in your VS Code, just do, you know, closing bracket and say add plots and hit enter. Okay, and that's going to take a little while because it's a pretty big package. But then once that's done, you can do using plots and make an empty plot like I did. So look, how beautiful is that, right? An empty plot, which does just nothing. Okay. So just to illustrate how the philosophy works, the package uses keyword arguments a lot. Okay, you remember we talked about those. And so, for example, if I want to add a title, I have to use the keyword argument title. Okay, if I say title and a string, then it's going to print on top that is the title. Okay, so now, of course, we want to add some data. So, right, so you can plot different objects, but I think it's best to always think about X and Y. X would be the X-axis, Y the Y-axis, and then you can plot different objects there, plot lines, dots, and so on and so forth. Okay, so let's just look at a couple of examples. So, for example, a simple line graph would be you have an X, you have a Y. Okay, so Y is just X squared, and you give it to the plot function as two arguments, X and Y. And then it's going to, by default, draw a line for you. Okay, so that's very basic and I think very similar to what you know from MATLAB.
Sorry, one question. What
Sure.
does this let and end mean? Do
Yes.
we see that?
Yeah, no, so it's a Pluto thing. So I do that here in order to create only local variables such that I can further down below, I can have another X and another Y again in a let block. Okay.
Okay, thanks.
Because that just means, look, if I do X here, there's no X outside of this scope. Okay. It lives only in the let block. It's
Sorry,
don't worry about
sorry.
this. Yes.
Another quick question, because I've seen this sometimes before.
Yeah.
To the power of 2
Yeah.
integer,
Yeah.
should it be 2.0? Just
No, it's because it's an integer power.
okay.
So no, not at all. It's
Oh,
totally
it's
different.
because the x is an integer.
The X here could be an integer, but that doesn't matter. So you want to put a 0.2 here?
Yeah.
Yeah, but that's something different. Okay, so the integer power is a well-defined mathematical operation, because you know what it is, right? It's x times x.
Okay.
Okay, and so
Yeah.
x to the 2.1 is something very different. Okay, people don't realize that, like from a math perspective, it's very different. It's a fractional power. Okay, so that's totally different. Okay, but you're right, you could do that. It will give you the numerically same result, but you actually don't want that here. I want just 2. I want to have the integer power. Okay,
Perfect.
Now, if we have installed these plots and
Yeah.
we write in this Visual Code, we write the plot with empty.
Yeah.
This we should get a result.
Yeah, if you do it using plots.
It will be an error.
No, it's not
Plots not defined.
good.
Using plots I have to write. Okay.
You have to do using plots, yes.
Okay, sorry.
So using plots, and then it should work. Okay, so here's that. All right, let's plot the matrix. Okay, so here I create some fake data with the thankfully defined function fake data, which is going to give me a 10×2 matrix of fake data. I call it FD, and I give that to the plot function, and it's going to plot 2 lines. Okay, so by default, if you give it a matrix, it's going to regard each column as a different series of data. Okay, and so in this context, it will not take the first column as the x-axis. It will think these are both y-axis. Okay, so you can see it plots 2 y lines. On the x-axis, you just have the index, first value, second value, third value, fourth value. Okay, so that kind of takes a little bit of time. Okay, so here there's basically the first argument is missing here. The first argument here is 1 to 10. That's the x-axis. Oops, 1 to 10, right? You see, if I omit that, it automatically says, yeah, you surely want to plot each row, okay, for how many lines that there are. Okay, so, and of course, if I give the first argument, the x-axis, I can change that. So it could be from -5 to 4 instead of from 1 to 10. Okay, just making this up. Okay, so whatever. This is just starting to build a little plot there. All right, something else that sometimes is useful is you can give an actual function, for example, a sine function, and you say from 2, so from 0 to 2 pi, plot the sine function for me, put a label. Look, this is again one of these special strings. It's called a latex string. I loaded before the latex strings package, which is going to print nicely for me latex here, so it knows sine x, and the label is a latex label as well. Okay, so that kind of sometimes looks nice, and you can use that. Okay, here we go. So that's the task. Actually, I already gave you a head start. So you're supposed to add the plots package, and say using plots and so on, and then you're supposed to write a function. Okay, and finally, write a function called fake lines n that will plot as many lines as given via n. You should use this funny function here, plots fake data, to make that fake data, and that's it. Okay, so you just want to have a function fake lines. If you give it fake lines 3, it should return a plot with 3 lines. Okay, let's try that. Just look at the example that I had just one slide before, and I'll open the the breakout rooms again for you. You can try that out. Okay, how did it go? We were able to make this plot.
How, the assert part, I forgot the assert part. How you do that?
No worries. So let's quickly see what we can do. So let's see, using plots was to get the functionality, and then what else? All right, so create this function fake lines. That's going to make that for us. Okay, let's create a function fake lines n. And okay, so first we need the data. What do I call that? FT, like fake data. And then we use plots fake data. So we just have to, well, how many do we want to do? 12 by n maybe. We wanted to actually assert something before. So assert that n is less than 10. Otherwise the plot is going to get too messed up. And then we just want to return this thing as a plot. And we can say a title. Well, what do we want to do? We do n nice lines. So you see, we interpolate the n into this title string, and then we have this function. Okay, fake lines. Let's try it out. Fake lines, two fake lines, and so ideally that should now pop up here. In okay, so you see this is compiling now. First plot always takes a little while, but then they go much quicker. Okay, so here two nice lines. Show very sharp now for some reason. Well, so let's try fake lines 11. Okay, error, assertion error. Great, that's what we wanted. 9 fake lines. Okay, good. Right, so that worked. Everybody happy with how we did that? Yeah.
Can I ask something? We were discussing this with Luis. What we did is we put the plot fake data inside the plot function directly.
Okay.
And but still I get allocations. So I still get that there are like 3.93k allocations in the function. And also we put in the argument for the function, we define it n to be an integer.
Yes.
But it doesn't seem to make any difference with the other, at least in time.
Yeah, no, I wouldn't expect there to be massive gains here. And so also, you know, the performance of plotting is not our main concern. It's not our bottleneck, right? I mean, we're not.
Yeah, no, sure. I was just wondering if
no, it's a good point.
This,
so I wouldn't, you know, that package in particular is not known for its speedy execution of stuff, right? So I wouldn't spend too much time trying to make it fast or not.
Okay.
So I mean, here, you know, you just go. If it goes as quick as this, you just hit the button and it comes out, and it's good enough.
Yeah, but and where do the allocations come from? It's from the plots, or is it from the fake data that it actually allocates the data?
Yes, for sure. That's going to be one allocation. So definitely, because that creates an array, right? So
yeah, but we were not creating the array. We were putting directly plots.fake data within the plot function.
Yeah, but still.
Still, okay.
Okay, so that's the whole point. So it's mostly about those hidden allocations, because as a user, you think, well, I'm not saying anywhere fd equal to some array, but still to perform the computation, you do need to store that array somewhere. Okay, otherwise you will never be able to plot the plot. Okay, so that makes sense that you see an allocation happening.
I'm getting problems with the assert.
With
I
assert? What does it say?
It says load error, assertion error, stack trace, fake.
So maybe, what did you say for assert? What does your assert line say?
Exactly like the same as used. N smaller than 10.
And so you give an error if you give n bigger than 10?
Yeah.
So you verify that it works, assert. So assert works if you
Yeah, sorry.
if you're Okay, good. So let's keep going. Good. Let's build a couple of plots. And one thing that I really like about this package is that you can build plots step by step. So you can start with something and build it up in a stepwise fashion. Okay. So for example, you can start with this and here. So the sign again, and we assign it to a variable, to P. That's the same plot as before. And now I'm going to put something on top of that. Okay, like this. Again, you remember the exclamation mark. So we will modify the input argument, which right now is a plot. So I will just overplot that with the cosine function. Okay, same. This is cosine, so it's going to look like that. Okay, and like this, you can obviously then create very articulate plots, and it's nice to see. I find it a nice workflow to see how this thing builds up, so you can kind of have a lot of control in designing the plot, as it were. You can also do it in one go without having to assign a variable. So for example, here in my little let block, I first do the sign and then I do plot exclamation, which will by default overplot the previous plot. Okay, so then, and I can have a title, which is going to be we put for, so the title keyword goes on top of the overall plot. And you can also add the other, so there's these other functions which work like keywords, but you can call them outside. For example, Y label is going to put a label here. Okay, so that's simple ways to build up these plots in a stepwise fashion. Okay, now the whole thing with stepwise plots has a direct corollary, which is animations, because an animation is the same thing as overplotting a plot several times. Okay, and so that's the idea that they pursued here. It's very easy to do this with this package, and I'll show you how. For example, here's one. You don't have to do much. You create a plot, which is going to plot the sine and the cosine function at a certain point, 0. Okay, so this just plots one point, and you fix the x limits and the y limits of that plot such that the scales don't move. And you create what is called an animation object as part of the plots package, and you will just push onto P, which is the plot, a new point x. Right? So you go over the x-axis like this, tuck, tuck, tuck. You follow these lines basically. You trace out the x-axis, and you record the value for sine x and cosine x. Push that onto P, and then you create an animation. You say this is a frame of the animation, like you take a snapshot, and then you call the GIF function in the end, and it will return to you something like this, which is very simple, but can be very interesting. Okay, so that's just to show you how to make a quick and a dirty animation out of your plot. Right, so of course, all of those things, how should you know them? So whether you call it title or I don't know what. So you need to confront a little bit the documentation. All of these things are called attributes in the plots package. So it's this page of the documentation that you should look at. So it's a really, really big section. So these are all of the various attributes that you could have. So attributes pertaining to series, to the entire plot, to subplots, etc. So you have to kind of look a little bit around here. Most relevant for us, I guess, are series attributes. So here are all the attributes you can give a series, like a vector of data. What could happen with this? And you see that all of these things, thousands and thousands of things, whatever. So I always search for stuff here. So color. So you see line color. These are all the different keywords you can give to line color. AC, L color, A color, line colors, line color. They will all work, and they will all pick up the color of the line. Okay, so just line style, should it be dashed or not? I don't know. Line width, should it be thin or thick, etc., etc. Okay, so you usually spend a lot of time on this page here, figuring out what is the attribute you want to set as a keyword on the plot. Okay, and then some attributes work with some backends and some don't. Okay, so sometimes you are in this situation and you say, okay, well, particularly in 3D settings, sometimes some backends find it hard to, for example, change the camera position and stuff like that. I found that a couple of times. But anyway, there's some situations where some backends don't take all the keywords. Okay, and in particular, I find this very good. This page here, which is the examples page for the GR backend, which is very good. And we'll now go over some examples from this page, just to see how they did it. Okay, so let's go with this. Let's get our fake data again, and let's change the marker shape keyword. Okay, without marker shape, you saw there was just a line. Okay, so where there was no marker shape, a marker is this thing, dot. Okay, so we say now at each data point, put a marker and give it this shape circle. Okay, it's going to draw a circle for each dot. Okay, so that's good. Now let's do, if you have two series, so you remember that's two columns in there, you can give attributes to each series separately. Okay, so now I have row vectors, those have to be row vectors. First series should be a circle, second series should be a star. Circle, star. Okay, and this is kind of the main idea. So with this, obviously you can do everything. So now let me do a different color for each marker. Okay, so first series has a green circle. Second series has a yellow star. Okay, and so on and so forth. So now you can change the size of those and the line width and I don't know what. Okay, so for example here, you can collect those things together. So the marker now is going to have a shape, a color, and a size. Okay, shape, color, and size for each column of the data array. And the line, you give them as tuples, line type, color, and size. Okay, so so that you can then combine these things and make this as exactly as is to your liking in this kind of way. And of course, all of the other arguments, the other attributes that we just looked at on that website, they can be put there to further customize this. Okay, and I said you can, it will accept very short versions of this. Instead of marker, you can write M. Okay, if you're very adventurous and you will then remember what M meant, you can just write M as well. Okay, so let's do something. Let's upgrade your fake lines function, and let's add a label to each line, such as line I for line number I. Okay, and also give them a different marker shape. You can look here at this page what the different marker shapes are. Okay, so if we had our function here, fake lines, so this function now we want to change so that in this call here, we need to do something. So basically we want to change that stuff. It shouldn't read y1, y2, y3. Instead it should read line I for line number I. Okay, so we need to change that somehow. Okay, you want to give it a try? Let's spend 3 minutes on it.
That was quick.
I was too quick, sorry. Sorry, guys.
Oh.
You want a bit more time?
Yeah.
Yes. Sorry. Well, you just keep working on it.
Yeah.
Yeah, I called you back because there's one slight issue that you may find a bit annoying, and it has to do with those labels. So how did anyone get that far that they can print the label stuff here?
No.
I managed to print label 1, 2, 3, but in the 3 lines.
Yes, no, exactly. So that's the point. So it's very annoying. I should have told you. So the labels keyword here, it wants a row vector. So everything you give to those keywords has to be row vectors because it wants to talk to different series, you see? So I'm sure what you didn't specify this as a row vector. Okay, but rather as a column vector. And so it's going to write the whole column. It's going to look terrible. So you want to write it like this. So you see, it's an expression, a comprehension that will say there's a 4i, but I is only 1. So it's going to, write a matrix with 1 row, something we call a row vector. And so then it's going to work. It's going to map correctly the line to the thing. Okay. And so then that's almost it. And we also said we want to have different markers there. So how could we do that? So labels is this. We need to do marker shape. And then we need basically again we need a vector of marker shapes. So what do we have? We need to find out what those are. Marker shape. Okay, so I would just copy that stuff. Create a second function. Shapes. Okay, shapes is this. And now shapes. How can we do that? Because we have the same issue. So we grab those shapes. So I call that S shapes. 1, 2, N. My N shapes. And then I need to do this stuff here. So I need to say S J or I in 1. I think at least I have to do like that. Okay, so I would have created S, which is these shapes. So, these are all the potential shapes that we can have. So shapes, just give you back this thing of shapes. And now we want to get the first N of those. That we call it S. And then we want to do that as a row vector. All right, let's see if that works. Page lines 2. Okay, well, something was wrong. It did not work. The first line doesn't have a shape for some reason. Well, it's none. That was very smart. So I have to delete the none and also the auto. Let's get rid of this. Okay, so that's good. So we can do it like that. Maybe even simpler if you just put here auto, what's going to happen? I don't know. Maybe it's going to do it anyway. Maybe that's the right solution. Yeah, I think that's the right solution. Okay, just let him pick different marker shapes by saying auto. Okay, that's going to automatically put different markers for each line. It's going to look like that, and so that's going to be very nice. And we like that. Okay, good. So, okay, good. So let's try and finish in style. Let's put a bit more colors onto this, so we can also have a Z line and Z marker. So not only X and Y to be mapped, but also a third thing, Z, which we can color stuff with. Okay, for example, here we can add a color bar on the right, which is the Z value, and we can color the color of the markers, for example. Okay, so Z marker would color the value that corresponds to each marker. So for example, here again, fake data. This is the same. We now said a marker Z, we give the data to this marker. So that's just values from 10 to 1 in descending order. And it's gonna, each marker is gonna get a color corresponding to that value. Okay, so as always, row vectors, we said first line, second line, and so on. So that's gonna mark the marker with colors. You can do the same line with Z, line Z. Okay, so here, for example, we do P1 plot X, Y. There's just some X and Y values, no legend. And in the second here, so line Z, that colors the line with T. T is this array. So those values from 0 to 1. And the second plot, P2, is going to have a marker. As a marker Z, it's going to have a function. So that's very cool. See, it takes the plus function. And so it will map X and Y with plus. So here what you see is X plus Y, that makes the colors, you see. Top right is going to be the highest value. So that's the lowest red, for example. Okay. Bottom left is the lowest value. So it's the bluest blue. Okay. So that's kind of nice. You can do that. Of course, you can just give a data series here as well. Okay, what's also cool is that we put two plots next to each other, you see. So without much effort, we just created a plot with two panels by just calling plot again on two plots. P1 and P2 are both plotting objects as we did them before, but we can just combine them. Calling plot and putting them together next to each other. So that's cool. So we can easily build subplots. Okay, so let's look at that. Okay, that we do very often. And so let's quickly look. There's a keyword that's called layout, and you can give it several arguments. For example, you can give it a sort of grid specification. So that would be 1 by 5. Okay, layout 1 by 5 is a 1 by 5 panel, which would maybe look something like this. Okay, so here we plot something, some random normal data, 100 values for, so it's a 100 by 5 matrix, 5 columns, which means 5 series here. We have a plotting type for each series. You see 5 different types of plots: line, histogram, scatter, step array, bar, etc. We say no legend. We say a layout, okay, 1 by 5, and whatever, no border and no ticks, for example. Okay, so we can be more sophisticated here. We don't have to stick to 1 by 5 layout. So suppose we give these names A, B, C, D, E to these different subplots, and then we can arrange them however we want with the layout macro. So look, and we can use the bracketing syntax like if we were to create an array. Okay, so look, this is going to create a matrix. So a matrix where the first column is the plot A, which is 0.1 of the height of the plot. Okay. So that's going to be this guy. It's going to be 10% of the plot height. That's how we write it. Semicolon means next row. So next row of the plot, up from here downwards, is B. B is full size of the remaining space. Next to that, there's another matrix where C is on top. This is C. Next line, D and E at the bottom. Okay, so you can in this way very flexibly build and very quickly build complex plot layouts. Okay, so here was that. That's it. And then you just give this L to the layout argument. So the L is layout here. Okay. And okay, then you can add a title to each subplot, maybe 1, 2, 3, 4, 5. Just like this. Each plot gets a title. Okay, we put it on the right title location, right, and so on and so forth. So you can customize that to your liking. And you can even want to have more fine-grained control. So for example, suppose I want it like this, but I don't want the numbers here, the y-axis labels, because it's too small. It would look terrible. Okay, I just want it like this. Here I want the y-axis labeled, but not here. How could I do that? Okay, so it's again very easy because we can build the plot step by step as we saw before. So that's true here as well. So let's quickly see how we could do that. It's very simple. You would get your data from somewhere and you would create an array which is empty, an empty array like this. And then you can push plots into that array. Okay, so let's start pushing into plot array. The first is our first plot, the plot right at the bottom. First column of data, no ticks, that's what we wanted, and title 1. Okay, the other ones, here are the plot types: histogram, scatter, step rate, bar. You iterate over those, so that's from 2 to 5. Push each plot into the plot array. Say what each plot should be. It should take the ith column of the data thing. It should be a certain series type, right? Which were here. Other types, no legend, and a title. But should have ticks. So I didn't say ticks nothing because I want the ticks on the y-axis. And that's it. In the end, the last thing you do, you put it together. You call the plot function again. You give the plot array as an argument. Notice the splatting operator, because I want to insert each plot as a separate argument. And I want to say what layout to use, where to put the titles, what font to use on the titles. Okay. So in this way, you can see, you can be very, very flexible. So you can work on this little plot, you know, make it green or red or blue and I don't know what. And in the end, when you're ready, you just push it together and then, you know, arrange it on a panel like that. Okay. What's useful is often to link axes, particularly if we have subplots, right? So look at this. We want definitely that the left and the right panel have the same y-axis. So there's a keyword for that. It's called link. So you can say which axis to link. So in this example, I wanted to link the y-axis such that those are on the same scale. Oh, wow, here's a big exercise. I'm not sure we want to do that. So I think that I'll leave that to you. It's a very cool exercise. I spent quite some time to think about it. It's a lot of fun. So, but I'll let that to you. Okay. So that's for your leisure after we're done. And that, yeah, that's the end of that. So let's use the last 10 minutes rather to quickly show some interactive plotting, which is very cool. So don't forget about that exercise. It's really cool. It talks about Santa Claus and Rudolph the Red-Nosed Reindeer. So that's quite something, I would say. And so we go back there to just finish with interactive 7, maybe interactive. Okay, so that's much the same idea. So, you know, plots and stuff, but now we go into the Pluto environment. So that's in this last session, we'll actually use the Pluto notebook to do some fancy plotting. Okay, so maybe what you want to do in order to get used to this a little bit is to start Pluto and look at the sample notebook on the Pluto UI. So this package I'm loading all the time, which has these nice elements like the slider in it and all of these things. You can easily use them. So if you start Pluto, like I did here, right? You remember, you say Pluto run. After you said using Pluto, it will bring up this browser that I look at all the time. So it brings up this thing. The first thing you can do is look at the sample notebook. So we won't have time to do that, but just go at this and open a sample notebook and it tells you which ones. And I would suggest you look at the Pluto UI sample notebook. It's really fun. It's always playful the way they do it. So it's quite cool. Okay, we won't do that. We'll quickly look at how to build a nice interactive plot, okay, for something that may be useful for us. Okay, why is that interesting? It's interesting, I think, because it's very easy to do. I mean, you can do those interactive apps with everything you want, right? With MATLAB, with R, it doesn't matter. Some are more or less user-friendly, but I don't think it gets much more user-friendly than what you can do here. So look at this. So here's a plot that's going to use a variable r and plot x to the r, to the rth power. Okay? Plot, this is a function, it's an anonymous function from 0 to 2. And we're going to, that's it, plot that function. Now the crazy thing is that r is connected to this object here, which is this slider object, which we give a range and some options, and the bind macro connects those two. And so now I can grab this slider and move it around, and the plot replots each time I move the slider. Okay, and so this is very simple, and indeed it is, but that's basically all you need. Okay, so you can now use these objects and integrate them into your notebook, and you can show your co-authors how this function behaves when you do this and that, and so on and so forth. So let's try this out. Let's look at the SIR model. The SIR model, you must have heard of this if you lived through the last 2 years. I'm not sure where you were otherwise. So of course, that's the epidemiological model. It's short for susceptible, infected, and recovered. So, and you can think of it just as 3 bins, 3 buckets of people. And people can move from one bucket to the other with a certain probability. Okay. And of course, what we'll look at here is total toy model. And the real models are much more complicated, but it will do. So we have discrete time. STITRT is the number of susceptible, infectious, and recovered people in each time period, and N is the total number of people. And so on average, in this model, in each period, you can think of a uniformly chosen person. If that person meets an infectious person, and if that person is susceptible, which happens with a certain probability, then that person will get infected. Okay? If you are, and there's a probability associated to that even, so it's not sure that if you meet an infected person, you will get infected. Okay, so there's probabilities all over the place, and so on. So let's not spend too much time here. We're running short. I just want to show you what you can do with this. So you define some normalized variables. So this is the share of susceptible in the people, the share of infected, the share of recovered. This is how the infected evolve. It's just very, very basic. Okay, and then you end up with this system of equations. 3 equations that tell you tomorrow's susceptible is today's susceptible minus the ones you lost to illness. Okay, probability of getting infected if a susceptible meets an infectious person. How do infectious people change? It's infectious today, plus how many come and got infected, that's those guys, and how many you lose because they recover with probability G. And then recovered is recovered yesterday, plus the probability of recovering of those that are infected. Okay, and so basically, we have this very simple system of equations which we want to simulate over time. We're going to step over this. So here's a simple way you could do that. Just set some numbers, 100 people. Let's say 99 are susceptible in the first period. 1 is patient number 0, it's infected, and 0 are recovered. You normalize this, so you have the shares. You set a probability to pass the infection on, and you set a probability to recover, and then you're good to go. Right, here's a discrete SIR model. It takes those numbers in, it runs it for 1,000 periods. It does exactly what we just said, so let's not waste time on this. Just does this simulation. What's the new S, new I, new R, and it collects the results. Okay, plot, that's what it looks like. Okay, so you have S blue, I red, R green, and you know, so you've seen these plots thousands of times. That's just what they look like. So that's all good and nice, but suppose now, how is this picture going to change if this probability of recovery changes? So what if we can change G? Now you look at this, even in this very simple model, it's not straightforward to pinpoint what's going to happen. I mean, I could not tell you by just looking at it. So let's make this a bit simpler for us. Let's just do something. So what does it say here? It says, remove G in the code cell above and add a slider for it right here. Okay, let's try. So G was defined here. All right, so we'll get rid of that. And we want to or rerun this cell. So G is no longer defined right now. Okay, G is used in this function. So when I run this function, it will complain. You see, it says, "Oh, G not defined." Instead, I'm gonna do this here. I'm gonna say I want to bind G to a slider that goes from 0.01 in steps of 0.01 all the way to 0.1. I want to show the value. True, I want to say default is 0.01. Okay, now I can grab this guy now. When I change it, the function will recompute and it will redo our plot. Okay, so we can also move with the arrows. We can see, okay, now that I increase G, the probability to move out of infected gets higher. And so this is the dynamics as you see them. Okay, so you can then study how does this system change if you change this one parameter. Okay, and so that's very powerful. I think that's a very cool tool for you to work with, and you should use it.
Florian, a question about the orders. You are defining G after you were calling the discrete SIR function?
Yes, exactly right. Great observation. So we didn't talk about this at all, but in Pluto, order doesn't matter.
Good, okay.
Let me just grab this guy and put it wherever I want, down here. Okay, so order is totally irrelevant. That's the whole philosophy of Pluto. In that sense, it's different from Jupiter. Jupiter is like a global workspace, okay, which means you define X and you do something with it, and then you make a plot. If you change X above, the plot will not change. Okay, so you have to be careful that the evaluation order is always preserved. So in Jupiter, most of the times you have to restart from the top. Make sure that the order is executed in the right way. It can lead to very weird bugs. So in Pluto, they said they don't want that. So in Pluto, everything, that's why you can only have one X, you see, because it's gonna know which cell depends on X. It doesn't matter where you put it. It just knows that if I move around this guy, some cell up there will have to update. Okay, that's Pluto. That's very good. Okay, now there's a continuous version of this, of course. This is the continuous time SIR. Now you just let this time step go to 0. You end up with this system of differential equations. This is, a system of ODEs where now you want to see how does the time derivative evolve of susceptible, infected, and recovered. So it's exactly the same thing, just in a small time step. And you need something to solve this. And so there's a very good ODE infrastructure in Julia, a very good, mostly, widely held as the best in the world. So it's very, very easy to use. So let's just quickly look at how you would do it. You would set up a function SIR, which will compute for us du, which is the change. So it's basically the left-hand side of this equation system. So here, the derivatives. We know how those work, so we just, we know what the system looks like. We know what the derivatives are, and that's it. Again, we modify the input argument. See, we return nothing. So I'm going very quickly, but it's not, you can look at the differential equations package if you need to use those things. That's just how you solve it. Solve this ODE problem, whatever SIR, that's the function, you start somewhere. And we hooked up those values to beta. So beta is the slider that goes into the ODE thing. And then I can move around beta and see what changes. Beta, gamma, all of these things will immediately compute the solution to the ODE system, which will then show up as a solution to the plot. Okay. So just to illustrate that this works very well and very speedily. So indeed, you can actually use it to make some sort of inference. Okay. So some sort of comparative statics on your model. And do it like that. Okay, that's the end. I say here a bit closer to home, but also I guess we won't have time to do that. So I let that for you to do it at home. So it's kind of a nice exercise, I think, because it shows you a econ domain. So in this exercise, you're supposed to do this kind of sliding business on an actual life cycle model, which is just below. So you can go down. Okay, here is the simple life cycle model. It's just a couple of lines. It's a nice illustration of the EGM algorithm, which you may know. So it's a way to solve a consumption savings problem. It works out of the box. So you don't have to worry about it. Just have to copy the whole thing. And the exercise you want to do, it would be to open a Pluto notebook, to put this in the first cell. So tell it that you want to use those packages. Then you evaluate the cell, which is going to load them. And then you would grab this code below, paste it over, and then your task would be to add 3 sliders to investigate the different values for sigma, beta, and R. Okay, you would just give them here as keyword arguments, and that would be your task. You could then easily do that to figure out. So this function here will give to you the savings function, the consumption function of this problem, which is a plot, and you would then change the sliders, let's say of sigma, which is the standard deviation of the income shock, and you will be able to trace out what happens to optimal behavior. Okay, and same thing with R. So what happens if the interest rate increases to optimal savings? You can see how these things change. So it's kind of a nice little tool to, I mean, it's perfect for teaching, by the way, if you ever have to teach that kind of stuff. But, you know, just I leave that there for you to have a look at. I'll put the solution, it's already on the repository, the solution to this. There's not much of a solution really. It's just, you know, it's very simple to add those sliders as you've seen. But anyway, I'll put the solution there. It's there already. Okay, so I'll clean up this repository now that we're almost done. And then it's going to be, all the solutions are in snippets. So if you go in there, there's one of those that's called interactive, you see here. And that's just a Pluto notebook that you can run at home and see what the solution was supposed to be. Okay, I think that's it from my part. End of workshop, 16 o'clock. So I think we're right on time. Any more questions before we say goodbye? Anything at all?
I think.
Oh. Sorry about the.
Say, do you have a question?
Yeah, because I was thinking in Jupyter, because I was working in Python with Jupyter, and I was thinking if I can use Pluto with Python, it is possible?
No, unfortunately
Okay.
not. Unfortunately not. So they took inspiration when they built the Pluto thing from something called observable, which you may do a search on that, but I don't think you can run it with the Pluto kernel, unfortunately.
Okay.
So, yeah, too bad.
Oh, yeah. Yeah.
By the way, I did never mention that, but the interoperability capabilities of Julia are really excellent. Okay, so if you have a big code base in Python, or you want to use a particular Python package, there's very little overhead for just calling that function from Julia. Okay, so that works very well. And indeed, many packages use that functionality. For example, so there's a package called PyCall, which is built to call Python functions from a Julia session. Okay, with very little overhead again. So there's no. Anyway, so I'm not going to go through that now. But there's no. It's not like, you know, I'm not sure what you could imagine when I say that you call Python, but it's not that you write a file or something like that. Okay, so it goes directly into Python and executes something in Python with the same data. Okay, so I think that's the main thing. So you don't have to copy an array over to Python, do stuff and bring it back. No, it's going to map the data in Julia or the other way around, and you do stuff in Python and you get the return value back from the function. Same with R. Okay, which is totally amazing. It's a package called rcall. .jl. It looks like this, and you can do stuff like that, for example. Okay, so you're in a Julia session, you say using rcall, which is this package, you say using our data sets, which is a data set. You get a data frame, empty cars, then you switch on the thing into the same REPL will switch into an R REPL. There's a shortcut. Then you're in R, you say library ggplot2, and you make a ggplot, and it will show up. Okay, and so you can go back and forth like almost seamlessly. Okay, so it's very cool. I use that actually quite often because, you know, as it happens, there's many R packages that are useful, like I don't know what, non-parametric regression, blah blah blah. And that works very well. So interoperability is very good. There's more of this sort. Even there's also MATLAB interoperability. You see here, you can call the MATLAB engine if you need to from Julia and so on and so forth. So that was a good question. Anything else?
I wanted to ask about optimization, especially if you have any recommendations about doing big problems.
Yes. So you mean many choice variables, non-differentiable?
No, I mean more everything differentiable, but very big, like on the order of thousands of variables.
Okay, but everything differentiable.
Yeah.
So, okay, so that's yeah. So I mean that we didn't touch upon at all. I can point you towards the lecture slide where we treat that. So I guess it's the third of this optimization series. I do 3 lectures on optimization because you understand it's such a big topic for many economists. And so the automatic differentiation capabilities of Julia are very, very good. Okay, and so that's what you want in these big problem cases. So I don't know exactly what your problem is, but you know, so if you think about machine learning, where what you want to do, you have like tens of thousands of parameters, and you want to take the derivative of a loss function with respect to all of those 10,000 parameters, you cannot do that numerically. You can't do finite difference approximation or anything like that. So you need automatic differentiation, which Julia is very good in. So I guess it's best if you look on this website here, which is referenced down here. I will improve that. Okay, so you go here, and then it's going to be optimization 2 or 3. 2. I don't know which of those 2, but you'll have to look. Okay, so there's going to be a bunch of references to do things. So it depends exactly what you do. If you have constraints or anything like that, there's a very cool package which you should definitely look at, which is called, it's down here, it's called Jump Dev. Okay, so that's like totally amazing. It's a modeling language inside Julia where you just write your problem out and it will transform it into stuff. It will automatically differentiate it. It works for like millions of choice variables. Okay, so it's very, very powerful, and I can recommend strongly. Again, it depends what exactly your problem is, but big problems that are differentiable, definitely Julia is a good bet.
Okay, thank you so much.
Yeah. Any more?
I just want to thank you, Florian, because it was a great course. I think
Thanks for
we really learned a lot. There is a lot to be learned still, but
yes, no, of course. So I know 8 hours are very little, but it seems that at least you got a starting base, and now you can start exploring yourself. And obviously, you know, you'll have to look at other people's code and stuff. But I think, you know, because you all know very well how to program, it's going to be kind of easy to switch in case you got interested now, or to know that you want to stay away now that everything you've seen. That's fine. Okay, good. So see you around, maybe in person next time somewhere, hopefully. And
sure. Yeah.
Best wishes to Barcelona.
Thank you so much, Florian.
Thank you.
Thank
Bye.
you.
See you
Okay.
guys.
Bye, guys.
Awesome.
Have a good one.
See you.
Bye.
Thank you.
Bye.
Bye-bye.
Bye.
Bye.